Hi Year 12, so we're looking at finishing off this methods of proof stuff. So we did last time sort of geometric proof. We looked at questions where you've kind of done things before, but then it was just proving that this always equals this. You had this identity in the middle, things like that. If you remember that one was the nastiest one, we haven't seen that before really. And those are called proof by deduction. So there are a couple of other methods that we have to kind of show you on this. The first one is called proof by exhaustion. Now, last week in the lesson, I said that one of the things that you cannot do with maths is just sub things in. So for example, if I wanted to prove that n plus n equals 2n, what I couldn't do is just start subbing numbers into it and say, okay, well, if n is 2, that's 2 add 2, which equals 2 times 2 is 4. So it works. If n is 3, 3 add 3 is 6, 2 times 3 is 6, so that works, and then say, right, so it's true. And that's because there is an infinity of numbers that you would have to do that with to mathematically prove it. However, there is a method of proof called proof by exhaustion. Now that is effectively the opposite of what I've just said. That's saying that you can prove it by just subbing everything in. But what happens here is that the cases that you can sub in are limited. So if we have a little look at this, there's a kind of an example here in this top paragraph. For example, you can prove that the sum of two consecutive numbers between 100 and 200 is an odd number. Now, two consecutive square numbers. Now, there aren't many square numbers between 100 and 200, so it limits the number of things that we would have to trial this with. So if you look, the only square numbers between 100 and 200 are 121, 144, 169 and 196. Now we can add the consecutive ones of them, can't we? So we can do that one at that one, which is 265, which is odd. Then that one at that one, which is 313, which is odd. And that one at that one, which is 365, which is odd. So we've done all of that. We've proven it by exhaustion. We've said these are the cases where this can work, that fit the criteria of the question. Here's me proving with each case that it works. So therefore I've proven it by exhaustion. Okay, that works when you are given a constraint. So like that. If it just said prove that the sum of two consecutive square numbers is an odd number, then that becomes very, very difficult. Okay, well, not very, very difficult, but you couldn't do it like this. You would have to use algebra there. But because it's saying that you've got square numbers between 100 and 200, then you can use proof by exhaustion. Okay, so that's what that is sort of stating there. If it's asking you to prove it for all numbers, you can't use proof by exhaustion. But if it asks you to prove it for a set of numbers between two constraints, two limits like 100 and 200, then you can do that. Right, let's have a look at example 12 then. Prove that all square numbers are either a multiple of 4 or one more than a multiple of 4. So what this means, this now is all square numbers, so there is an infinity of square numbers. Remember, if there's an infinity of numbers, you can square them off. There's an infinity of square numbers. So to be able to prove something like this, what we have to do is try and split them down into specific cases. Okay? All numbers are either odd or even. Okay? So if I can define an odd number using algebra, and then define an even number using algebra, if I square both of them, then hopefully it'll give me something that I can then link it to being a multiple of 4. Now, you might have done this in GCSE, but if you didn't, you need to remember this. If we're ever proving something and we want to do a method like this, or for any other method, if we want to define what an even number is, we call all even numbers 2n. We call all odd numbers either 2n plus 1 or 2n minus 1. I'm going to call them 2n minus 1. Okay, so I'm now asking to prove that all square numbers, so if I square these things, is a multiple of 4 or one more than a multiple of 4. So let's multiply these things out. Okay, so if I do this one, remember that becomes 2n minus 1 brackets 2n minus 1, which is going to give me 4n squared. 2n times minus 1 times 2n is going to give me minus 4n, and then plus 1 at the end. Okay, now I can prove that that is a multiple of 4, or sorry, one more than a multiple of 4, because if you look at these first two terms, I can take 4 out as a factor of that. So that part is a multiple of 4. because I can factorise out 4. So when I square an odd number, it's always one more than a multiple of 4. There's my even number, so when I square that, I will get 4n squared. So because of that 4 there, that one is a multiple of 4. Okay, so we've done it. So if they're asking you to prove something about kind of all numbers and you're thinking, hang on, Sarah said that we can't do that, try this method. Try splitting it into all the odd numbers and all the even numbers, and define odd like that, define even like that, and then see if you can work your way through the algebra. Right, the next thing we need to look at is counter examples. These are dead easy. You just need to find one specific example that disproves what you're being asked about. So, prove that the following statement is not true. The sum of 2 consecutive prime numbers is always even. So what this means is if I can find 2 consecutive prime numbers that add up to an odd number, I've disproved it. Now if you think about your prime numbers are 2, 3, 5, 7, 11, carry on like that. So what we need to do is find 2 consecutive ones that don't add up to an even number. So let's try these two. 7 add 11 is 18, so that does prove the rule. 5 add 7 is 12, so that does prove the rule. Can't use them ones. 2 add 3 is 5. Now 5 is odd, so that disproves this. 2 plus 3 equals 5, and then you would have to state 2 and 3 are prime. 5 is not even, so therefore we've proven what we wanted to prove. Remember that from last week, QED, that Latin phrase that means we've proven what we wanted to prove. Okay. Right, this one. Okay, so prove that for all positive values of x and y, x over y plus y over x is greater than or equal to 2. Now, these ones are trickier, okay? What I would advise you to do with something like this is try and manipulate the algebra to get it into a format that you can deal with. Now at the minute we do not like fractions, so what I'm going to do here is I'm going to add them fractions together by cross multiplying. So if I times the bottom two together, I'm going to get xy on the bottom, cross multiply it, I'm going to get x squared plus y squared, and that's going to be greater than or equal to 2. So to get rid of this thing, I can turn that into x squared plus y squared is greater than or equal to the xy, I'll just come up there, 2xy. And then I'm going to make that equal 0. So I'm going to write this as x squared minus 2xy plus y squared. Right, now I might be thinking, why have you put that minus 2xy in the middle? And hopefully you might be able to spot something from that. This factorises. Okay, and hopefully you can spot what it is. If you can, well done. If not, I'm going to go through it in a second. But this thing factorises. So if you couldn't spot it there, factorises into x minus y all squared. Okay, so we've now got it into something where we can start making statements about it, because what do we know about when we square something? Whether it's positive or negative, it always turns positive. So, go back to the original statement. Prove that for all positive values of x and y, this, which we've manipulated into this, is true. So effectively now we can say, prove that for all positive values of x and y, x minus y all squared is always bigger than 0. Okay? So, if we just write down, when x and y positive, x minus y all squared is always positive. So we've proven there what we wanted to prove. Okay, right, and then part B, use a counted example to show that this is not true when x and y are not both positive. Now, this doesn't particularly help us then, because whatever way we choose, remember that by manipulating like this, whatever happens in the bracket there, whether we have whether x is plus or minus or whether y is plus or minus, we will get either a positive number or a negative number in there, and then we're squaring it. So this format of the original inequality doesn't really help me. I'm going to go back to the original one. X over y plus y over x is always greater than or equal to 2. Okay, so I want to disprove this when they're not both positive. I want to disprove it using a counter example. So if we let x equal minus 6 and y equal 2, let's see what happens. We're going to get minus 6 over 2 plus 2 over minus 6 is greater than or equal to 2. And that's going to give me minus 3 plus minus a third, which is greater than or equal to 2, which is going to give me minus 3 and a third, which is greater than or equal to 2. Therefore not true, and we've proven what we wanted to prove. Okay, so if you get given algebra like that at the top, what I would do is kind of just jot down some workings from it. Ask yourself, what can you do with it? If you've got fractions, clear the fractions. If you've got you know, something that looks like it can be factorised, try factorising it. If you've got brackets, expand the brackets, get it all over onto one side so it equals 0, so you can manipulate it. Think about the things that you could do with the algebra. Try and sort of manipulate it into a format that you can see, and then ask yourself what that format tells you. So when we manipulated it to like this, we have the bracket squared is greater than 0. That anything squared will always give us a positive number, so that proves that this thing is always greater than 0. Second time, when it's asking for a counted example, just see if you can spot a counted example. Okay, and that's it. So once you've kind of copied all that in, can you choose, let's see, from this one, right, have a go at the odd numbers in the next exercise, please. Okay, you can use to exercise 7E, and I'll email the link to the solution bank home for you as well. Okay.